Hi there, welcome to this lesson 2C-6, and we are going to talk about non-periodic context and modeling it, specifically looking at logarithmic models given a context. In this lesson, we will look at FRQ number 2 questions, where we have to write and solve a system of equations. We'll also look at modeling logarithmic regression lines given a data set, and then we'll go ahead and look at given questions in context, how we can answer those questions. This does require technology, so I am going to be utilizing Desmos as well as a TI Inspire. I'll try to switch between the two in order to give you a look at both of those technologies, okay? So, jumping right in, a logarithmic model can be used to model situations that have proportional growth, where your input values change proportionally. So you multiply times a period of time, and then your output increases at an even or equal length value interval. Okay, the logarithmic model y equals a times log base b of x can be constructed from two input-output pairs by creating a system of two equations and then solving the system for those constants a and b. A is generally your initial value, and then again b is your base. So just a reminder, you can do this with technology, and you can also solve systems of equations via substitution or elimination. And substitution is when you take one variable, you isolate it, and then you plug it back into the other one to create a new equation. You solve that. Once you have one variable, you can plug that back in. There are some notes here about how you create regression models for TI Inspires. If you want to pause and look at these notes, you can go ahead and do that, but I'll kind of walk through those as well as in Desmos, okay? So let's go ahead and look at the first example here. Example 1 says, in a wildlife reserve, the population of gazelles has been increasing at a decreasing rate since 2002. In 2002, t equals 0, there were an estimated 450 gazelles in the reserve. In 2008, t equals 6, there was an estimated 670 gazelles. The population of the gazelles in the wildlife reserve can be modeled by the function g of t, where g of t equals a plus b times the natural log of t plus 1, where g of t is the number of gazelles t years after 2002. And so they say write two equations that can be used to find constants a and b. So they give us two data points. The data points that they give us are t and then g of t. This is the number of gazelles, and they say at time 0 there's 450, and at time 6 there is 670. So for some of these questions they give you the data table, sometimes they don't. So I like to organize it because then I can just plug stuff in. So my first equation is going to be 450 gazelles is equal to a plus b times the natural log of t plus 1, so 0 plus 1. So there's my first equation, and then my second equation, 670 plus a times b, or a plus b times the natural log of my t value, which is 6 plus 1. So that's all you need for that first point, and this is, again, FRQ number 2. B, they want you to go ahead and solve. So usually with this one, what's nice with a logarithm of 1 is that that is equal to 0. So if I go ahead and simplify this equation, 450 is equal to a plus b times the natural log of 1, this is 450 is equal to a plus b times 0, because the natural log of 1 is 0, which implies that my a value is equal to 450. So I found my first value. Now I can go ahead and I can take that value and I can plug it into the 670 equation. So here's my second equation. 670 is equal to, well, I know a now is 450, so I'm going to substitute that value in. B times the natural log of, I think that's 7. So what we do have to do here, though, to find b is we have to solve this. So I'm going to go ahead and just do some inverse operations. Subtract 450 on each side. And what we get is then 220. Ideally, if I had enough room, I'd go straight down. 220 is equal to b natural log of 7. And we can divide by natural log of 7. And we get b This implies that b is equal to 220 over ln of 7. And again, I'm going to go to my calculator and I'm just going to plug that in. So 220 divided by natural log of 7, and we get 51.783. 51.783. And there's A and B. Pretty smooth, pretty smooth. Oh, actually I had a typo. That's not what we had. I typed in 7D, not 7. So natural log is 7. So 113.058. 113.058. Okay. Cool. Here is a practice problem. Same idea. So please go ahead, read this context, and then write 2 equations, and then solve for the constants A and B. I'll show you the answer here in a second. Okay, here are your 2 equations. Hopefully you got 2,240 is equal to A plus B times the natural log of 0 plus 1. And then 2,410 is equal to A plus B times the natural log of 5 plus 1. There's your 2 equations. Part B, you can solve for A because the natural log of 1 is 0. So essentially they give you A equals 240. And then we can plug that into our second equation. I just replaced A here, right? And so instead of A, I have 2,240. And then we can go ahead and solve. We'll subtract the 2,240 from both sides, and that should give you 170. And then we divide both sides by the natural log of 6. Natural log of 6. And you get a final answer, 94.879. Remember, you must round or truncate to 3 decimals, okay? So hopefully you got that one. We're going to go ahead and we're going to look at a regression problem now. They say the table gives information about the age t in years and the average height h in meters of a particular species of tree. They say the data in the table can be modeled by a logarithmic regression of the function h of t equals a plus b times the natural log of t. So given a data here, the first thing you want to do with Desmos, I think Desmos is the easiest, is make a table. So if you go ahead again, click plus, make a table, now we can enter this information. So 1, 2, 3, 4, 6, 8, and then we can enter the outputs 1.83, 4.02, 4.57, 5.34, and 5.8. We now have our data. Okay, and there we go. There's our data. I fixed that. No 2 in this, so I erased the 2. And now, in order to create a regression, we just click this little line with the dots next to it. Boop. Click regression. And what will happen is you'll have a newly constructed line function that goes through your data points. Now, I don't want a linear regression. This is a straight line. I want a logarithmic regression. So I'm going to click logarithmic regression. And they give us our values right here. So there is your logarithmic regression equation. Now please note, do you see this log mode here? Go ahead, turn that on. Sometimes that will adjust your equation, and it's important to note that other calculators, other TI calculators use logarithmic mode. So if you click this little help button, they'll explain more to it, but generally you want that on, I've noticed, to help with some of the aligning some of the answers. So make sure that's ticked on if it is there. If your question has a question about residuals, you can go ahead and plot residuals, or if you're going to need to use this function, you can go ahead and click this little button right here, and it will export this whole function into another line, and I can now use this line. And what I like to do with this is I like to go ahead and rename this. Now our function is talking about the height of a particular species of trees, and so they call it h of t, so I'm going to rename it h, okay, based upon that function. And again, I don't use t, I always use x, because Desmos and TI likes x. So there is our equation right there, and then there's our values if they ask for it. Okay, so let's see what they want. They say A, when as a decimal approximation will the average height of the tree in years reach 8 meters? Okay, so what they want is they want 8 meters. And what I like to do for these questions is I always like to identify the inputs. What is our input? Well, our input here is based upon time in years, and our output is height in meters. So they're going to give you information and they want you to solve for something. So here they say, when will the average height of a tree in years? So that's a clue that I need to go ahead and I need to solve for t. I don't know what t is. And then they say when the tree reaches 8 meters. So what they're telling you is h equals 8. Okay, so essentially what I want is I want to know when will h of t be equal to 8 based upon this regression. So what we do is we go ahead, we have h of t equals 8, and I can solve that via graphing. I'm just going to graph the line y equals 8, and I'm going to have to zoom out a little bit and check it out. Bingo, there it is. So that value, t equals 24.214. Okay, all right, there you go. That's when. Next, B, find h of 10 and explain what it means in terms of context. So again, here your input, this is time, and so they want us to find h of 10. Well, again, we can go to our calculator, and now that I already have it defined as h, I can say, hey, calculator, what is h of 10? And they tell me. So h of 10 is equal to 6.298. 6.298. Okay, there it is. And what does this mean in terms of the context? So I always have, whenever they say, what is this in context, I have the acronym CUT. I always use the acronym CUT. So the C stands for context. What are we talking about? So h of t, let's say here, h of 10 means the height, or the average height, of the tree at t equals 10 years. Okay, and there's your time. There's the time. The t value is time. So when? And then is what? Will be 6.298, and then here it's going to be meters. And then the U stands for units. So context, units, time. So my context, we're talking about the average height of a tree. The units, well, at 10 years is the time, and then this value is in meters. Okay, so there you go. Pretty straightforward. All right. If you wanted to know how you do a logarithmic regression in a TI Inspire, here's my TI Inspire. You have to make a list first. So I have to go here, I have to label each column, and then I'm going to enter that same exact data. So 1, 3, 4, 6, 8. And then my output values here, I'll call Y, and we get 1.83, 4.02, 4.57, 5.34, 5.8. And then now I'm going to go just next to one of my boxes, and I'm going to go Menu, Statistics, Distributions, and then I need to go to, why is it acting funny? Is it not Statistics? Is it Data? Statistics? Oh, Stat Calcs. For some reason that was off. And I want a logarithmic regression. So you got to go down, and there's logarithmic regression. Again, Menu, Stat Calcs, and then logarithmic regression. And what you have to tell your logarithmic regression is, hey, I want to use my X list is going to be X, what I title X, my Y list is going to be Y, and then they say, here, save the regression to, and that will save your regression, kind of like what we did, how we brought it down in Desmos, to this function, f1. Okay. And then, so here's your values, and if you'll notice, if you add a graph, is I can graph that function. So VAR, I have my function right here, f1 of x. So there's my regression equation, and it will graph it. So then I could go ahead and answer that question, hey, when will it have a height of 8? Okay, and we can, find that intersection there. Menu, analyze, intersection, left, right. Okay, and then we can also use a calculator, add a calculator, and I can evaluate that function at 10, right? So they said, what is what will be the height h of 10? What is h of 10? So there's my function h, f1, again stored under VAR, and then I hit enter, and it gives us that value, 6.297. Okay, just kind of more steps with this. Desmos is a little bit more cleaner, but again, that's how you do it in a TI. Okay, let's look at the very, very last couple of questions. It's in context, very similar to what we just did, except we don't have to go ahead and do a regression. So here's a practice problem. They say the number of unique species of plants in an area of California can be modeled by the function S of A. So there's your context, which is equal to 77 plus 147 log of A, where S of A is the number of unique species of plants in a region with an area of A square miles. So here's the question. In what size region will it be expected there will be 150 unique plant species? Express your answer as a decimal approximation and include units with your answer. So I'm going to go ahead, pause video. I want you to answer this question, and then I'll talk through the solution. Okay, here you go. They wanted the unique species of plants to be 150, so you can set your function equal to 150, and then we can go ahead and solve. A will be equal to, I graphed my function s of x, and I graphed 150, and you just have to zoom out a lot to find this intersection, and there it is, 3.138. And the units, remember, this is square miles, so miles squared based upon our question. Okay, so did you get it right? Just note too that you could have done this right algebraically. You could have subtracted 77, and then you get 147 log of A is equal to what does that give us? 73. And then you can go ahead and divide, right? Log of A is equal to 73 over 147, and then raise both sides to the power of 10. 10 to the power of 73 over 147. So you could do it algebraically as well. 10 to the power of 73 divided by 147. Okay, and you get the same exact value. Cool. All right, next question, B. How many unique plant species, there should be a T there, can be expected in a region that is 10 square miles? Express your answer as a decimal approximation. So go ahead, answer this question, and I'll show you the answer. All right, hopefully you got 224 plant species, and that is because they want 10 square miles, so that's your input value, there's your A. So you plug in 10. You could go ahead and evaluate this, but log of 10 is just 1, so you get 77 plus 147, which is 224. Pretty straightforward. Okay, next question, B. The function B is given by B of M equals 500 over 1 plus 0.005 e to the power of km, where k is a constant. They say if B of 4 is equal to 180, what is the value of B of 9 as a decimal approximation? Pretty tricky here. So I'm going to go ahead and I'm going to kind of talk through this one. Because this is weird, this is really like a two-step problem. One, we have to find what k is, and they do that with an initial value. So when they say B of 4 is equal to 180, they're saying, okay, 180 is equal to 500 over 1 plus 0.005 e to the power of k times my input, which is 4. So m is 4, and now that's k. Okay, so what I'm going to go ahead and do is I am going to graph this. So I first want to go ahead and graph my function. So let's call this b of x equals 500 divided by 1 plus 0.005 e to the power of 4x. Okay, and now I'm going to go ahead and graph 180. And their intersection, that will be your value of k. So there is k. Now what I want you to notice is k has a lot of decimals, 1.46842. And so I'm going to go ahead, and you can do this too, is you can take this value, you can copy it, and you can say, hey, k equals, and I'm going to call it that value. So now what I can do is I can copy my function, and I have this value stored, and so I'm going to replace that value with k. Okay, so I'll turn this one off. And so what I've essentially done is I've solved that initial value. I know what k is now, and now I have my old function back in here ready to be evaluated. So x is our old m input, right? So I use this. I solved for k. Bink. Okay, and then now my function b of this function b of m, they want to know what's b of 9. So b of 9 is going to be equal to 500 divided by 1 plus 0.005 e to the power of k times 9. Okay, and so we'll use graphing technology for that. Now that I have my function defined, we can go ahead and say, okay, what is b of 9? And let me get rid of this one. There we go. Okay, and there we have it. This is 0.182 as a decimal approximation. All right. Okay, there you go. Hey, in this video, we went ahead and used graphing technology in order to look at solving some logarithmic models, making systems equations, solving those, using regressions, answering questions, and then just modeling using technology about logarithmic situations. Okay? Hopefully you liked the video. Thumbs up. I'll see you in the next one.